Let's dive right into this explainer and look at one of the absolute most fascinating paradoxes in clean energy today. We're always hunting for innovative ways to power the grid without pumping out greenhouse gases, right? We talk about building massive new infrastructure, opening up brand new mines, basically reshaping entire landscapes. But what if one of the most powerful solutions to our future energy needs has actually been sitting right in front of us, literally since the dawn of the nuclear age?
Just imagine, for a second, if we could get 100 times more energy out of the exact same resources we're already mining, processing, and storing. I'm not talking about doubling our efficiency, not tripling it, 100 times more energy. That is wild.
So naturally, this brings up a massive question about the physics and the future of our global power grid. How on earth can a reactor possibly get 100 times more energy out of the exact same fuel? Well, to answer that, we've got to look closely at how our current technology operates and, honestly, where it falls surprisingly short.
Because here's the crazy reality. Our current standard water-cooled commercial reactors leave a staggering 95% of the uranium fuel completely unused. Think about that for a second. We do all the heavy lifting to mine and process this incredible energy source, and then we only extract a tiny fraction of its power before labeling it as waste and scrambling to find a place to bury it deep underground. It's literally like buying a full tank of gas, driving to the grocery store 3 miles down the road, and then just tossing the rest of the car in the garbage.
To understand exactly how we fix this massive inefficiency, we'll be following this roadmap for today's explainer. First, the nuclear status quo. Then, what is a fast reactor? Next, fast reactor superpowers, followed by a history of innovation, and finally, the global clean energy race.
Starting with Section 1, the nuclear status quo, moderating our potential.
So, the crucial starting point is figuring out where our technology currently stands. The vast majority of global nuclear power plants today are what we call thermal neutron reactors. Now, thermal here doesn't just mean hot. It means the neutrons are actually in thermal equilibrium with their surroundings. See, when an atom splits, it shoots out these incredibly fast-moving neutrons. But our current reactors actually use a moderator, usually just normal light water or sometimes heavy water or graphite, to act like brakes. The water physically slows those neutrons way down so they can more easily trigger uranium-235. That's the specific, relatively rare type of uranium atom we currently use for fuel. In fact, a slow neutron is about 1,000 times more likely to split a uranium-235 atom than a fast one.
But using water as a brake pedal comes with some really massive compromises. Since water boils at a relatively low temperature, these reactors are kind of bottlenecked. They're limited to operating around 300 to 350 degrees Celsius. Plus, because they're only targeting that one specific uranium-235 isotope, they only tap into a tiny fraction of the available uranium energy. The rest? Well, that becomes long-lived nuclear waste filled with heavy, highly radioactive actinides. And that's the stuff that requires those deep underground repositories, staying radioactive for hundreds of thousands of years.
Which brings us to Section 2. What is a fast reactor? Taking the brakes off.
So, what actually happens when we stop slowing the neutrons down? By swapping out water for coolants that don't act as brakes, like liquid metals such as sodium or lead, or even molten salts, fast reactors keep those newly generated neutrons zipping around at incredibly high speeds. Because there's no moderator in the way, the fast neutrons smack into the rest of the unused uranium. You know, that 95% we've been treating as garbage. Well, it actually converts it into brand new fissile fuel right there inside the reactor. It's an absolute game changer.
Moving right along to Section 3, fast reactor superpowers, efficiency, waste, safety.
This simple switch in coolants unlocks what we can legitimately call superpowers in the energy sector. By continuously recycling this newly converted fuel, fast reactors can pull off a jaw-dropping 90% reduction in nuclear waste. We're talking about taking what used to be a multi-generational liability and literally flipping it into a massive asset.
Now, why this matters is deeply tied to the timeline of nuclear waste, which, let's be honest, has always been one of the biggest societal roadblocks for nuclear energy. Because the neutrons in a fast reactor are moving at such insane energy levels, they essentially act as a nuclear incinerator. They absolutely obliterate those long-lived heavy elements. So instead of needing to babysit this waste for 100,000 years, it decays back down to natural background levels in just 200 to 300 years. That is a manageable human timeline, not a geological one.
On top of that, liquid metal coolants have much higher boiling points than water.
This means fast reactors can operate safely at way higher temperatures, up to 600 degrees Celsius or more, without needing the crazy high-pressure systems that water reactors absolutely rely on. Because of this superior heat transfer, they can crank out up to 3 times the power density of a similar-sized thermal reactor. To put that simply, you get a much smaller power plant producing a massively larger amount of clean electricity for the grid.
And from a safety standpoint, these low-pressure systems are inherently safe by their very design. If temperatures unexpectedly spike, the metallic fuel physically expands. It just happens naturally. This thermal expansion spreads the atoms further apart, which automatically chokes out the chain reaction and shuts the entire reactor down. No human intervention needed, no active computer systems to fail. It just shuts itself down safely.
Which leads into Section 4, a history of innovation, decades of development.
Now, you might be sitting there thinking, okay, this sounds like pure sci-fi. Why haven't we built these things already? Well, actually, we have. This technology has been proven over decades of rigorous real-world testing. Looking just at the U.S. timeline, fast reactors produced the world's very first nuclear electricity way back in 1951 with the experimental breeder Reactor 1 out in Idaho. Its successor, EBR-2, famously demonstrated that exact passive safety shutdown feature in the 1980s. And the Fast Flux Test Facility in Washington spent a whole decade testing liquid metal reactor components. So the foundational physics and engineering, they've been thoroughly established for well over half a century.
And that brings us to our final section, the global clean energy race momentum building.
Today, as the world desperately chases net zero emissions and looks for reliable baseload power to back up solar and wind, we are seeing a massive resurgence in this proven technology all over the globe. The International Atomic Energy Agency recently gathered the global scientific community in Vienna at the FFR22 conference, and the overarching consensus was crystal clear. Bringing fast reactors and closed fuel cycles to commercial scale isn't just a neat idea anymore. It is now viewed as an absolutely vital, indispensable tool for decarbonizing our electricity production and hitting true sustainability.
The sheer scale of international deployment happening right now is incredible. It's a true global race. Russia's already operating large-scale sodium fast reactors, while China is actively constructing their massive CFR 600. India is finalizing a prototype of their own, and here in the U.S., major private companies backed by the Department of Energy are pouring heavy investments into new designs like the Natrium reactor. Everyone is getting in on this.
IAEA Director General Rafael Grossi powerfully summed it up at that conference, stating, "Fast reactors can be a bridge to even safer and more efficient nuclear power, providing sustainable, clean energy for generations. By making the absolute most of our natural resources and dramatically shrinking the burden of radioactive waste, fast reactors really do represent a bridge to a sustainable future, checking off the most critical boxes for safety, economics, and environmental stewardship."
So here's the final takeaway for you to ponder as we wrap up this explainer. We have a technology right now that extracts 100 times more energy, essentially incinerates its own long-lived waste, and safely shuts itself off if things get too hot. With this technology fully within our grasp and the demand for clean energy skyrocketing every single day, how quickly will the world actually embrace this high-speed solution to our energy crisis? Are we really going to continue leaving 95% of our fuel behind, or is it finally time to take the brakes off?